Greetings, my name is Hardik Raj, and today we will be discussing the problem Galactic Football. This is an easy problem, and the prerequisites are graph theory. This problem was asked in July challenge of 2013. Let's look at the problem. In the problem, we are given some connected components. Let's say that this is a connected component. Okay, and then another connected component might be like this, and another connected component might be like this. What we need to do is we need to connect this component with either this component or this component, and again this component with either this or this. Well, basically what we want to do is we want to select a node in each of the connected components, and let's say we selected this node and this node, and then we want to create a path. The path can be like this, or the path can be like this. So basically what we want to do is let's segregate the selected nodes. Let's say this node came from here, let's call it A node. Let's call this B node, this came from here, and let's call this C node, which is this. Now we just want to create a simple path like this. The cost of creating a path is somewhat that each node is given a weight or a cost. So the cost of A is, let's say it's CA, the cost of this node is CB, and the cost of this node is CC. Then if we create an edge between any two nodes, then the cost of that edge is CA plus CC. Or let's say we connect any nodes I and J, then the cost of connecting the nodes will be CI plus CJ. So this is what we have to do, but there are certain conditions. An edge can be formed between two nodes if and only if both Ci and Cj is greater than or equal to 0. This is the first condition. The second condition is all the components should be connected at the end. That is, a path should exist something like this, or it could be like this maybe, or it could be like this. Let me use a different color. The path could be either like this, or maybe this is also a path, this is a path, and even this is a path. Why? Because connecting this node and connecting this node, we can basically travel from this connected component to this connected component. Similarly, let's say it was connected something like this, then we could have easily traveled from this connected component to this connected component. All right, so that is our task. So then for creating an edge, the cost of the nodes should be greater than 0. Second, at the end, all disjoint components should be connected. All right, and one more condition is the total cost should be minimum. That is, the total cost of creating all edges, the total should be minimum. We have to minimize this. All right, so how do we do this? Let's look at the approach. Let's say we are focusing only on one connected component for now. It might be something like this. And each of these nodes will have a weight. Let's say it's -1, -2, -3, 1, 10. Okay. So what we want to do is from this connected component, we want to pick the minimum non-negative weight. Or let's say it was 0. So we want to pick this node, or actually this node. All right. Similarly, in the other connected component, let's say the cost is -1, the cost is -2, and the cost is -3. So since there is no non-negative weight, then we cannot join these two connected components, that is the connected component 1 and connected component 2. In this case, the answer would be -1. But let's say the cost was 2. Then what we want to do is we want to pick this node, because this is the node which has the minimum non-negative weight, and we want to join these two nodes, something like this. And the cost would be 0 plus 2, which is 2. And by doing this, we have to join all the connected components. So let's say what we have done is we have, say, 4 connected components, and we find the minimum node in each of these connected components such that the minimum node is non-negative. Let's say the value was 2. Let's use a different color. Let's say the value was 2 here, it was 10 over here, 1 over here, and or no, let's say it was 7 over here, 10 over here, 6 over here, and 2 over here. And we want to connect each of these connected components such that a path exists. That is, we are able to go from 1 to 2 or 1 to 3 either directly or indirectly, or 1 to 4. Similarly, we should be able to go from 2 to 1, 2 to 3, 2 to 4. I hope you get the idea. So this is something like a minimum spanning tree. That is, we can consider each of these as individual nodes, and we want to add edges such that it is possible to go from one node to other. So this is something like minimum spanning tree, but not exactly, because here we have to consider not the edge weight but the node weight. All right. So in this case, what will be the optimal approach to find the edges? What I'm going to do is I'm going to pick, or rather, let's say the cost of creating an edge between nodes I and j is ci plus cj. What we are going to do is we are going to pick ci, which will be the minimum possible. So in this case, we will say that okay, we have fixed this node, and through this node we will create edges from like this, and the cost of this edge would be 6 plus 2, which is 8, 10 plus 2, which is 12, and 7 plus 2, which is 9. So the total cost would have been 12 plus 8 plus 9, which is 29. And see, here we can go from 2 to any of the other connected components. Let's say we want to go to 3. What we will do is from 2 we will go to 4, and then from 4 we will go to 3. Similarly, if we want to go from 1 to 2, first from 1 we will go to 4, and then from 4 we will go to 3. So yeah, that's it. And how to calculate this effectively? So this is a pretty neat trick which I will be explaining in the code itself, that what will be the total cost. So let's look at. So yeah, what we are doing this in this code is Since there are no test cases, I will be calling this solve function only once. And in this solve function, first we create edges between the given nodes. In the question, it is already given that some of the nodes are connected, right? So we have first connected those nodes. Then we need the cost of each edge. Sorry, we need the cost of each node. Cost of each node, which is Ci. For DFS function, this is a visited array. All right, int count equal to 0. This is the number of connected components. In this case, count was 4. In total, this will be the total cost. Actually, not total cost. This will be the cost of individual contribution. That is Cj. Do you remember that I said that the cost is nothing but Ci plus Cj? And here I was fixing Ci to be 2. That is the minimum cost, right? And we were adding Cj. So what total stores is, total stores the count of C1 plus C2 plus C3 plus C4. This is what the total stores. But this is not the total cost, right? Because the total cost would have been C1 for connecting component 1 to component 4, the minimum component. We need to do something like C1 plus C2, right? Again, C1 plus C4. Again, if you want to connect C2 to C4, the cost would have been C2 plus C4, right? Again, C3 to C4, the cost would have been C3 plus C4. And we don't want to, a self loop is not possible. That is, we cannot connect C4 to C4. In this case, we should have done minus C4. And that would have been the total cost, right? So this is what we are going to do. First of all, we are going to add the individual values, that is the minimum values. And in those minimum values, we will add the connected components minus 1 times. Okay, let's look at the code. It will be a little difficult right now. Okay, so this is the cost of individual contribution, that is this thing. This was total. Okay, int global mini. So this stores nothing but the minimum cost of a node which is non-negative. Yeah, so minimum non-negative node in all the connected components. All right, and this flag variable, this says if connected, if any connected component does not have a non-negative node. In this case, it would not be possible to connect the rest of the connected components with that component. All right. Now what we do is we call for each node, we see whether or not it is connected to any other component or not. If the visited value is greater than 0, this is actually simple DFS. What I am doing is I am first picking a node and I am visiting all the other nodes which are connected to this node. All right. But if this node is already visited, then that means this is already a part of a connected component and was already seen once before. We do not need to see it again. That is why if the visited value is greater than 0, we just simply continue. Int mini is equal to int max. Stores the minimum non-negative node weight or node in current component. Alright, so we call DFS with the current node and mini. I will say what the DFS function is later on. And now we check. Okay, let's look at the DFS function right now. So the DFS takes two parameters, the current node and the current minimum non-negative node in the current component. So we first mark the connected component, the current node as visited, and if the cost of that node is non-negative, we update the minimum value, and then we recurse for its children. All right. The important thing to note is we are updating minimum only in case of non-negative nodes. So if the minimum value was int max, and in the question it was given that each node will have a maximum weight of 10 power 4. So if the minimum value was not updated, then that means in this component, in this component there's no node which has a non-negative edge weight or non-negative node weight. So this might create a problem, or we will see when it will not create a problem. So we just mark the flag as false. That is, yes, there, or actually it should have been false, and here it should have been true. That is, we found a bad component. All right, and we were simply adding total plus equal to mini, right? And even in case of uh, int max, we are just adding it for now. Or we can say that if mini equal to int max, then don't do anything, or rather let's leave it for now. Okay, we are adding infinity over here, just keep it in our mind. Okay, and we increase the connected component by 1, and we increase the global minimum. All right, now let's see if we encountered a component which has no non-negative weights, but what if there's only one such component, that is all the nodes are connected, that so there are no more than one component that needs to be connected. So the number of connected components is only one. In that case, it doesn't matter if we have negative edge weights or not, or negative node weight or not. In this case, uh, sorry, if count equal to 0, or if count equal to 1. So it doesn't matter. It doesn't matter if we have non-negative nodes or not. We simply see out 0 because we don't need to create any external edges. Else, if the number of connected components is more than 1 and we have encountered a bad connected component, in this case the answer is -1. Else it is count -2 into global mini plus total. Now yeah, for this formula, basically what we are doing is, let's say that we had 4 components again, 1, 2, 3, 4. All of these components are good, and we have C1 plus C2, C3, and C4, where Ci is the minimum non-negative weight in that component. So what we want to do is, and in this case, let's say that C2 is the minimum amongst C1, C2, C3, and C4. So the optimal connection would have been C1 plus C2 plus C2 minus C2 plus C3 plus C2 plus C4 plus C2. This could be C1 plus C2 plus C3 plus C4 minus and plus 1 2 3 plus 3 times C2 minus C2, or basically C1 plus C2 plus C3 plus C4 plus 2 times C2. Alright, this was uh, our summation Ci I equal to 1 till 4 plus 4 minus 2 times C2. Okay, let's say we had four, 5 components, 1, 2, 3, 4, and 5. The cost is again C1, C2, C3, C4, C5. Let's say C4 was the minimum. In this case, the total cost would have been C1 plus C4 plus C2 plus C4 plus C3 plus C4 plus C4, or rather, we don't want to introduce a self loop, so we can just write 0 plus C5 plus C4, or rather let's write it that C4 minus C4, okay, and plus C5 plus C4. This minus indicates that we are not introducing a self loop. Okay, so the total cost was what? Summation Ci I equal to 1 till 5 plus 3 times C4, that is this thing cancels with this thing, and then we are left with 3C4. So the final formula after generalizing it for n connected components is summation I equal to 1 till n Ci plus n minus 2 times C min, where n is not the number of nodes, that's denoted by alpha. Okay, alpha, and where alpha is number of components. Okay, so let's try summating this. So as you can see, the solution was accepted. Let's look at the space and time complexity. Complexity analysis. In this code, we are visiting each node every once, right? So for the DFS function, for for this DFS function, we are using O of n, where n is the number of nodes. All right, and we need to store the nodes also. So we are using 3n extra space. So O of 3n. So this is the time complexity because of DFS, and O of 3n or O of n is the space complexity. So yeah, that's it for this question. I hope you understood, and see you next time.